Hi, everybody. So in this video, we show how a single vector field, so namely the intermediate eigenvector field of the Cauchy strain tensor, is able to highlight both elliptic and hyperbolic Lagrangian coherent structures in 3 dimensions. This goes all under the name of unified LCS theory, and for computational purposes, we'll be definitely looking at the Unified LCS ABC Study Analytic Notebook. So the two notebooks are exactly the same. The only difference being that here we will use the analytic velocity field, whereas here we will use the discrete gridded velocity field. However, as you will see, the computational burden in the analytic, so using the analytic velocity field, is already substantial. So I will just go through the analytic case. However, the discrete gridded case is really exactly the same, just replacing the analytic velocity field with the interpolants of the discretely gridded velocity field. So let's check out what this is actually all about and why it is useful. So again, we will be looking at the steady ABC flow for the moment. And the idea is the following. So the idea is that it emerged through the years that attracting, repelling, and elliptic LCSs are codimension 1 surfaces. So basically in 3D, these would be 2-dimensional surfaces, which always need to be tangent to the intermediate eigenvector field C2. So what this says is that no matter if you're looking for elliptic structures or for hyperbolic structures, so these structures, these surfaces, the tangent space of these surfaces always needs to contain this intermediate singular value field of the gradient of the flow map, which is equivalent to the intermediate eigenvector field of the Cauchy strain tensor. So this is a very important statement because it essentially allows to look for LCSs, no matter if hyperbolic or if elliptic, but it allows to look for LCSs in 3 dimensions by simply exploring this intermediate singular vector field. So the way we proceed is we look for structurally stable invariant manifolds of this equation, of this ODE here. So we pick, again, a grid of initial conditions, which will be our Poincare section, and we run trajectories not of the original velocity field, so not of this one here. So we don't use the classical Poincare map, but we basically apply the Poincare map to this ODE. So we compute trajectories from this ODE, and then compute the Poincare map for these trajectories. Again, we choose the z=0 plane for this. This computation is fairly involved because you can imagine that so first of all, it needs to be very precise. So because these eigenvector computations are numerically pretty critical. So one thing is that whenever you compute the gradient of flow map, you need to really make sure that you choose very fine-scaled temporal and spatial derivatives. So that's the first thing. That's why the computation takes more than 4 days on a very strong computer, which I was running it. So we need to compute first of all trajectories of this ODE, and this is simply done here. So we just simply define a grid of 20 times 20 initial conditions. We will, of course, choose the z=0 plane as we've done for the classic Poincare section. And then we simply compute these tensor lines, which we call, so tensor lines are simply lines which are tangent to this eigenvector field. Of course, in the computation of tensor lines, a critical aspect is that whenever you do the integration, you make sure that you locally reorient the eigenvector field so that you can continue the integration. This is the same as in the 2D case when we are computing the stretch lines or the shrink lines. There we also have to make sure that during the integration, so that after each integration step, the local vector field is oriented correctly so that we can compute, we can continue the integration smoothly. So we have here, for example, our auxiliary function, which is simply called parallel tensor lines, which takes input the initial condition. So this will be basically these 20 times 20 initial conditions on our z equals 0 plane and the dummy time interval here. We proceed then by simply computing these tensor lines using this function here, which essentially, so the integration is done in Runge-Kutta fourth order. We cannot use a standard ODE solver because of the issue that we need at each time step locally reorient the eigenvector field so that we can continue the integration. And the functions here are all pretty involved. So what this function does is it essentially computes the gradient of the flow map given over some time interval at this point here. The gradient of the flow map is computed by using the gradient of the velocity field. So here we make essentially use of the equation of variation and compute the gradient of the flow map using the equation of variation. And of course, here this function here, what it does is it checks the orientation of the xc2 vector and simply then reorients it if you during the integration. So what essentially all these functions do is they make sure that you can have a tensor line which is tangent to this vector field here, integrated over a very long time interval. So as an output, you get here the tensor lines, which are essentially trajectories of the above ODE. You can see the computation here took really a substantial amount of time. So that's like more than 4 days, which is huge. And you can then again, once you have these trajectories, you can sample these trajectories and you can check every time they reintersect that the z equals 0 plane, you can keep track of that reintersection. And what you get is the following structures where you can see here, okay, these two vortices. Now, in order to get a better visualization, what I would need to do is I would need to make the time step even smaller or run the integrations even longer. However, as you can see, it already took me 4 days to run it. And I wasn't willing to wait for longer. But if you want to be more precise and see better structures, you can actually run this of course for longer times. Interestingly, you have got these ridges here. So you have got this ridge here, which is not visible from the classical Poincare map, but this ridge here, as it is highlighted in this paper, in the pioneering paper where this approach has been introduced, this ridge here is associated to hyperbolic LCSs. And here you have the main elliptic ones. Of course, if you run the integration for even longer, I can show you the results from the paper. What you will approach is, let me scroll down. Yes, so you will approach here this Poincare map here. So it will look like this. And as a comparison here, you have the classical Poincare map. So of course, you can see that in the classical Poincare map, this structure here was not visible at all. Whereas this hyperbolic structure here, which is also visible from the FTD field, because also in the FTD field, you see that there is some ridge here. So the xc2 really shows this hyperbolic structure, which has been hidden in the Poincare map. And additionally also highlights these vertical flow structures with much higher detail. Again, I invite you to, if you have time and the patience, then you can run this for longer and make the time interval so the time step even smaller so that you're more accurate. If not, I would like to conclude this video. And again, I would like to point out that the structures you get here are far more detailed than the structures you would get from the classical Poincare map.